Okay, so this will be a video on integration by parts, which is another technique of integration. It's something that we resort to when we have an antiderivative to do, and it's not something on our list. So there's a formula for integration by parts. It's right here. But to use the formula, I'm going to talk about these 4 steps. So you're given some integral or some antiderivative to do. The first step, if you're going to choose to use integration by parts, and I'm going to get into why you would make that choice later, but assuming that's the choice you're going to make, you have to identify 2 parts of the integral you're being asked to do, and part of it you're going to call u, and the other part you're going to call dv. And that's referring to the formula we're ultimately going to use. I'm going to get right into how to make good choices, and this is, again, I have to give you the same warning that I gave for substitutions, which is that it's impossible to give you advice that's always going to be good advice, but in general, these things, like this advice, will rarely steer you in the wrong direction. The way I remember this is LIPTE. And what these are, these are the priorities for you, and these are in order, meaning if I see, so L is log, that the L is first, so that's my first priority, meaning if I see any logarithms in my integral, that's my first choice for u. If I don't see any logs, then I move down the list. The next thing I look for is any inverse trig functions, your arcsines, your arctangents. If I see any of those, I'm going to make those u. If I don't see any of those, I move on down the list. If I see any polynomials or powers, meaning like x squared, x cubed, square root of x is also a power, x to the minus 1 is a power. And those would be my next priority. If I don't see that, I move on and check for any trig functions. Those can be a decent choice for you. And then my last priority is any exponential functions, any e to the x, anything like that. And yeah, I just remember LIPTE. Once you determine what you're going to make u, the rest of everything is just called dv. Everything has to be there, whether it's in u or dv. So whatever you make u, dv is just whatever's left. The next step is to find du and v. Of course, the first step was to find u and dv, and so once I know that, to get du, I'm just going to do the derivative of u. And to get v, I'm just going to integrate dv. So that's what I do to get step 2. Step 3 is to just use this formula. And just like u substitution, when you use integration by parts, it's not really a magic bullet. It doesn't take care of all your problems. You always have another integral to do. In the end, it just takes whatever integral you have and it gives you a different integral. And you're always just hoping that the new integral is easier to do. And you just have to cross that bridge when you come to it. But we'll get there. Let's do one. So where are my priorities? I don't see any logarithms. I also don't see any inverse trig functions. I do see what I would call a power of x, and that's this x in the front. So that's going to be u. And like I said, dv has to just have everything that u doesn't have. So u was this x, so that means dv is the rest, e to the x dx. So we're good with step 1. We've determined u and dv. Let's move to step 2. du, I'm just doing this derivative, so it's just 1. and I'm supposed to write a dx there. For v, I'm doing the antiderivative of e to the x, which is just e to the x. And by the way, when you're doing integration by parts and you're finding v from dv, there's no point in putting a plus c here. Yeah, I won't even write it. But often when we do an antiderivative, we write plus c, but there's no point in doing that when on this step. When we get to our final answer, I'm going to put plus c, but there's no point in putting it here. Okay? Now I'm going to use this formula. So this integral that I started with is equal to u times v, so that's x times e to the x, minus the integral of v du. So v was e to the x, and du was just 1 dx. I won't write the 1. So we're there. And now I'm at step 4, and this is like I was saying, we always hope that the new integral is something we know how to do. As it turns out, this new integral is just something right off of the list. The antiderivative of e to the x is e to the x. If you follow this advice, and if you've made good choices, and if you aren't just very unlucky, you should be in good hands. This advice should usually guide you to a situation where the new integral is at least somewhat easier than the old integral. And that worked out for us this time. Antiderivative of e to the x is e to the x, and like I said, I'm about to just put a box around this and call it my answer, but before I do, I should remember plus c. You do want to put plus c on your final answer here, just not here. Okay, let's do another one. X squared natural log x. So I'm going to let u be something from my list of priorities, and the first priority is logs. So I do see a log. dv is going to be everything that wasn't part of u, so it's going to be x squared dx. Now I need to find du and v. This is step 2. Derivative of ln x is 1 over x dx. Antiderivative of x squared is 1/3 x cubed. I don't put a plus c here. And so this integral becomes, I'm doing step 3, I'm using this formula. It's u times v, so that's natural log x times 1/3 x cubed, minus the integral of v du. Integral of v du. Like that. And this is always the, slightly scary part. Like I said, the advice that we're following should always lead us to having a new integral that's easier than the old one. And so I look at this, I know that this is supposed to be doable, or hopefully it is. And yeah, maybe if I clean it up, it will be, because I cancel an x, and then I'm just going to have an x squared. I'm not too worried about this 1/3. That can come right out. So after thinking about it for just a moment, I'm not worried. Let me write this first part. Whoops, I'm a little bit off camera here. So I wrote the first part this way, and then I won't try to do too much at once. Let me just pull the 1/3 out and call this x squared. Like that. And then I've got a 1/3, and then I'm going to have another 1/3 x cubed. And at this point, I've done all the antiderivatives, so I'm going to put a plus c. And I guess I should clean this up. This is the part I am too bored to pay attention to, but 1/3 times 1/3 is 1/9. So all right. Yeah, so let's do another one. And maybe this one kind of looks a bit weird. Like, well, one thing that looks weird is often integration by parts. One big clue that it's a good idea to use integration by parts is that you see multiplication happening. Because what is integration by parts really? It's like two functions multiplied together. You've got u times dv, and so we always run into these examples where I have a function times another function, like x times e to the x, or x squared times natural log x. I'm used to seeing multiplication, and that can be a hint to use integration by parts, but I don't see that here. And that can be okay. There are some situations where you won't really see multiplication. Of course, in the end, I can sort of say that there's multiplication. I can just, say that there's an invisible 1. I'm multiplying by an invisible 1. So it's not too hard to like sneak multiplication in there, but this might not jump out at you. It might not scream, hey, use integration by parts on me, and yet it's still a good idea. I'm going to follow the priorities. I don't see any logs, but I do see inverse trig, so that's my priority to make u. dv is then, it's just everything that wasn't part of u, and that includes the dx. So actually u had everything except the dx. So I'm just going to say dv is just dx, and that's okay. By the way, to get du, you have to actually remember the derivative of arc sine. I will go ahead and just tell you what that is. This is not the most I don't want to make excuses. You should remember this, but this is out of all the things you can forget, this is a likely thing to forget, the derivative of arc sine. By the way, if you look at that PDF of things to memorize, there are derivatives to memorize as well as antiderivatives, and this is one of them. So assuming you remember that, we're good on du. To get v, I just have to do the antiderivative of this, and this is like, there's an invisible 1 here, I guess. The antiderivative of 1 is just x. Okay. So this integral is, I am using the formula that's here. So it's uv minus the integral of v du. So uv minus the integral of v du. Okay, and now here's the scary part. We're hoping that the new integral is something that we actually know how to do. And this, maybe, I'm not, I've definitely been happier, I'll say that, looking at what we're looking at here. This is not something that I recognize off of the list of antiderivatives to memorize. So I have to figure something out here. And this is where, so all the techniques of integration, they interact. Like you might have to use one technique when you're in the middle of another technique. To do this one, I'm tempted to use a substitution because, and one reason why is because I see a composite function. I see this denominator of a fraction with a square root and then something inside of it. That kind of jumps out at me is to say that it might be a good idea to do a substitution where u is 1 minus x squared. And let me stop myself right there because I said u. I'm going to avoid using the letter u again. I've already used the letter u for this, so I'm not going to call this a u substitution. Let's call it a w substitution or something. But the letter doesn't matter so much. So what did I just say? I'm going to do a w substitution, and what's a good idea to make w? It's the inside of a composite function like this. dw would be negative 2x dx. So I can go here. So I just write that down, minus integral of, okay, here I go, and I'm trying to complete the substitution, right? I'm not too sure what I'm going to do with this x, so I'll just leave some space. I'll figure that out later. I do know that this is u. That's the whole point of me making it, or whoops, w. But that's the whole point of why we made w what we made it. And so, right, so I haven't taken account of this x, and I also haven't taken account of dx. So let me do the standard thing for dx. I just solve for it. So dx would be dw over negative 2x. And then I just have to keep in my memory that the space I left here was for the x. Now I'm not too scared of that, because now I can see if I just left that x the way it was, then that x is going to cancel this x. And then there's no more x's here, so that's like a completed substitution. Let's keep going. This is x, arc sine x. Okay, I've got a minus sign here. I'm going to pull a negative 1/2 because I've got a negative 2 in the bottom. So actually, let me call this plus 1/2 because the two negatives cancel. Integral of, okay, 1 over root w. We're about to do antiderivatives, and we like powers. Powers are friendlier than roots, so 1 over root w is the same as w to the minus 1/2. I like that better. Okay, and I'm ready to go. So I've got this 1/2, and then how do I integrate a power? I increase the power by 1, so now it's positive 1/2. And I'm also supposed to put the reciprocal of the new power in front. So the reciprocal of 1/2 is 2 over 1. At this point, I have taken care of all the integral signs. There's no more calculus to be done, so I'm going to write plus c. This is the appropriate time to do that. Finally, I just want to clean this up and replace, like I want my answer to be in terms of x's. So I'm going to replace w. So x arc sine x plus, of course, this stuff cancels, and I get this to the 1/2 plus c. Okay. Let's do another one. X squared sine x. So let's take a look at the priorities again. I don't see any logs. I don't see inverse trig. This isn't inverse trig. This is just trig. Inverse trig is like arcsine, arctangent, that stuff. And trig is a much lower priority. So I don't see logs. I don't see inverse trig. I do see a power of x. So that's going to be my u. So u is x squared. dv is sine x dx. du is 2x dx. V is the antiderivative of sine is negative cosine. Okay. And this becomes, I'm just using this formula again, uv minus the integral of v du. So uv minus the integral of v du. Let me clean that up a little bit. Negative x squared cosine x plus 2x cosine x. Like that. The negative signs cancel and I just pulled the 2 out. Okay, and now what I always say is we look at the new integral and hope that we can do it. And now I'm a little worried. How do I do x cosine x? I don't see anything, last time this happened, we used a u substitution, or a w substitution, but I don't really see a composite function here. Like, I don't see, it's not like cosine of the square root of x or cosine of anything more complicated than that. It's just cosine of x. So I don't think I'm going to use u substitution. What I'm going to do is, and this is something that can happen, I'm going to do integration by parts again. So I'm going to sort of go off to the side. I was in the middle of something, but what I'm trying to do right now is I'm trying to do the integral of x cosine x. Let me just forget about everything else and just talk about the integral of x cosine x. We'll figure out what that is, and then we'll put that answer here, and that'll be our final answer. But let's just focus on this right now. In fact, let me put a little box around here because I'm about to do something that is, well, it's not that bad, but I'm gonna, just because, right, I don't like using the same letters again, but integration by parts, I'm just used to using the letters u and v, and I've already done integration by parts. I've already used u and v. I'm going to do another integration by parts here. I'm going to write u and v again, and as long as I do a good job of separating this stuff out, I'm not going to get confused between this u and v and that u and v. So in this box, u and v are going to be something different. Well, what are my priorities? I don't see any logs. I don't see any inverse trig. I do see a power of x, so that's going to be u. dv will be the rest. du is just the derivative of this, which is 1 times dx. V is the antiderivative of this, which is sine. and then I transform this. So the formula is uv minus the integral of v du. So uv minus the integral of v du. V was sine x, du was dx. And now, as usual, I say, well, I hope the new integral is something that I can do, and it is. This is something on our list. Integral of sine x is negative cosine of x. So I guess that would make this a plus cosine of x, right? Because I've got this negative sign, but the antiderivative of sine is negative cosine, so there's two negatives. So let's just remember that we were doing this side work so we could have an answer to put in up here. So let me continue where we left off. This was negative x squared cosine x plus 2. And then what goes in here is the answer that we just figured out. Oops, I need to write it down correctly. I'll distribute that to like that. Okay, so we did integration by parts twice in the same problem. That does happen sometimes. I know that at least one of you was just screaming in your head at me to do this a different way, especially because I did integration by parts twice. And let me get to that. There's a method that for doing integration by parts, and this method is fine even if you're only doing integration by parts once, but it's especially good if you're going to do integration by parts twice or 3 times. In particular, this is not an uncommon situation where you have some power of x and maybe it's times sine or cosine or e to the x. Whatever this power is, roughly speaking, it tells you how many times you're going to have to do integration by parts. Oops, I kind of messed this 2 up. Let me write it again. This was a 2. So because this was a 2, we had to do integration by parts twice. But if you see x to the 10th sine x, you're going to have to do integration by parts 10 times. I'm not really going to make you do one like that, but it can happen. So let me show you the quicker way. This is called the tabular method for integration by parts. And we're gonna do the same example that we did last time. We're just going to do it by this new method. So it was x squared sine x. And so I'm going to take the power of x and I'm going to write that in the u column. And I'm going to take the rest and write that in the dv column. Now I'm going to fill out the rest of these columns. This column I keep doing derivatives. This column I keep doing antiderivatives. So here I go. Derivative of x squared is 2x. Derivative of that is 2. Derivative of that is 0. And then once I hit a 0, I just stop. The rest of the column would just be 0, 0, 0 forever, right? Because the derivative is 0. So once I hit a 0, I'm just going to stop. Now let me fill out this column. Antiderivative of sine is negative cosine. Antiderivative of cosine is sine. Well, with this negative, it's going to be negative sine. Antiderivative of sine is negative cosine, but with this negative it's going to be positive cosine now. And then I stop because I'm at the same, you know, my 0 is across from me. I don't need any more than that. And now, how does this go? I'm going to do this times this, and I'm going to write a plus sign. And then I'm going to do this times this, and write a minus sign. And then I'm going to do this times this, and write a plus sign. And then, well, I could keep going, but this is the reason why we stop once we hit 0, because 0 times anything is 0. So I could keep going forever, but it wouldn't make any difference. So I stop once I hit the 0. And so what does this mean? I said I'm going to do this times this with a plus sign. So x squared times negative cosine x. And maybe just to emphasize, I'll write plus in front. That's this. Of course, that doesn't really do anything, but I'm just emphasizing like that's what this plus sign means. The next one would be, it has this minus sign, and then it's this times this. The next one would have this plus sign, and then it's this times this. And then I'm done. The next thing was the 0, so I'm going to write plus c like we always do at the end of an integral. And then let me clean this up just a little bit. I've got negative x squared cosine x. These negatives cancel, so plus 2x sine x plus 2 cosine x plus c. And that, just to remind you, is the same thing that we got the hard way. We basically did integration by parts twice, and we did it by hand, so to speak. But the tabular method will give you the same thing. All right. Let's do this one. I'm not going to do this one the hard way. I could do it the hard way. It would involve doing integration by parts 3 times, because this involves x cubed. But let's just not. Let's do the tabular way. Basically, I'm going to put the power of x here. I'm going to put this here. And then I'm going to fill out the rest of this column. And on this column, I'm doing derivatives. So 3x squared, 6x, just 6, and then 0, and I stop. Now I'm doing antiderivatives. And this is where, okay. How do I do the antiderivative of e to the 2x? This is a spot where maybe we're tempted to use a substitution, like let u be 2x. But this is why I'm just reminding you of this trick. This is from the u substitution notes. If you know an antiderivative, and I want to do a slightly different antiderivative like this, then I can do it. For example, antiderivative of e to the 2x minus 3 is just e to the 2x minus 3, but I have a 1/2 in front because of this 2. The antiderivative of e to the 2x is 1/2 e to the 2x. The antiderivative of that would have another 1/2. Of course, this 1/2 just stays in front, but I'm going to do the antiderivative of e to the 2x again, and that gives me another 1/2. That gives me 1/4 e to the 2x. And then 1/8 e to the 2x. And yeah, I'm going to do one more because I have to do, like, I have to have something across from the 0. I don't need to go below that, but I have to fill out as many as, like, I'm going to stop here when I hit 0. Whoops. I stop at this column when I hit 0, and then I stop this at the same level. So 1/16 e to the 2x. Okay, and then I multiply down the diagonals. So this is going to be like a plus. This is going to be with a minus. This is a plus again. This is a minus, and then I'll be done. X cubed e to the 2x with a plus. And then I'm going to multiply these with a minus. So minus 3/4 x squared e to the 2x. That's this. And then I've got this, and it's with a plus, so plus 6 times an eighth is 3/4 again. X e to the 2x. And then finally this times this. I can cancel it too, so 3/8, and it's with a minus, right? This minus 3/8 e to the 2x plus c. So it's not that bad. Not nearly as bad as doing integration by parts the hard way 3 times. Yeah, so, okay, I'm just going to leave you with a similar thing to what I said last time, which is like, of course, this video was all about integration by parts, and of course, we used integration by parts every single time, but in life, you're going to run across random integrals, and you're not going to know whether you should use integration by parts or something else. So how do you know, or how do you get a hunch that maybe you should use integration by parts? In general, when you see two functions multiplied together, that's kind of a good idea. Like, you just look at all of these things we did. We had x times e to the x. We had x squared times natural log. We had x squared times sine. We had x cubed times e to the 2x. There's a lot of multiplying functions by other functions, and that can be a hint to use integration by parts. You can also, with experience, you can sort of sometimes look one step ahead. Of course, the integral you start with is u dv, and then the integral that you're going to have to do after integration by parts is v du. So it's kind of like, if you can look at the integral that you're charged with the task of doing, and let me pick out an example here. Yeah, I'll just maybe look at this example, x times e to the x. And the advice I'm trying to give you is that you can look at this and maybe notice that you would rather do v du instead of u dv. Meaning that I'm looking at this integral, I'm picking it apart into two parts. One of them's u and one of them's dv. As it turns out, u was this and dv was this. And you can look one step ahead and say, if I did the derivative of this part and the antiderivative of this part, then what I would get is friendlier than what I started with. Because if I did the derivative of this part, it would just be 1, And if I did the antiderivative of this part, it would just be e to the x. And so I would just get e to the x, and that's something friendlier than x times e to the x. With experience, you can train your brain to do this. Of course, it can be hard, but it never hurts to just try and see what you get. If you can't look one step ahead, or you're not that confident, you can always just do the work and then see whether the new integral is any friendlier than the old integral. But it is possible to see one step ahead sometimes, and it's worth giving it a try sometimes. Of course, as usual, none of this advice is guaranteed to solve all of your problems, and sometimes trying things that don't quite follow the official advice will be successful. So if you feel like using integration by parts, if you want to see what happens if you try integration by parts, if you just don't know what else to do, those can be perfectly valid reasons to use integration by parts. You don't need some divine inspiration. You can just try it because you feel like it. All right.